Swayam Prabha. Digital India. Educated India.
Now let us go to the graph theory algorithm. Before going to discuss the graph theory algorithm, we have to know the fundamental concept of graph theory. So, the fundamental concept based on what is a graph and what is a path, cycles and trails, and next we have to interact the vertex degree and contouring, and then fourth one is directed graphs. And now once you know all these things, then we can understand where the graph is started. So, we have to go on Königsberg bridge problem. So, this is the this is one city X, Y and Z, all the cities. So, these are all the island. Okay, these islands connected by the bridge 1, 2, 3, 4, 5, 6, 7 bridges, and once you started from one bridges, you do not go back to the same bridges, do not cross the same bridge once again. Like that we have to cover all the 7 bridges. Is it possible? Then the problem is very difficult. This problem got it by Euler, and that then it is called as that Königsberg bridge problem they started. So, the Königsberg is a city on the Pregel river in Prussia, and the city occupied 2 islands plus area on both banks, and the problem whether they could leave home, cross every beach exactly once and return home. Now a model. So, we need a vertex is a region, an edge is a path bridge between the 2 regions. So, this is the picture represented. You have to start with E1 and go to E2 and then E3, E4 and then E5 and then E6 and then there is a block. So, E7. So, this is not possible, you have to cross one bridge once again, then only we will move to the E7. But we have a picture of the connection between the vertex and edges like this. So, the picture comes like that. Now, what is a graph? A graph is a triple consisting of vertex V of g and edge E of g and relation between an edge and a pair of vertices. So, this is the picture representation of connection between the vertex set and edge set. Next to loop. Loop is a multiple edges. Loop is an edge whose endpoints are equal. So, this is a loop, right. So, endpoints are equal. Multiple edges mean edges have the same pair of endpoints. So, this is the multiple parallel edges. Simple graph. A simple graph has a no loop or multiple edges. So, it is a simple graph. It is not a simple because it has a loop and parallel edges. Next, adjacent and neighbors. 2 vertices are adjacent and are neighbors if they are endpoints of an edge. Example, A and B are adjacent, whereas A and D are not adjacent. Next, finite graph or null graph. Finite graph means a graph whose vertex set and edge set are finite. Null graph is the graph whose vertex set and edge set are empty. So, next to complement. Complement G of a graph G is a simple graph. So, V of G dash equal to V of G. So, E of G dash equal to UV, UV not in the EG. So, that is the meaning of complement of one graph to the another. So, for example, you take a graph this one. Now, there is a no edge connection from U to Y and Y to X. So, there is a no connection with U and V, right. So, therefore, this is a complement of the graph domain to codomain G to G dash. Next, click and independent set. a click in a graph, a positive pairwise adjacent vertices. So, pairwise adjacent vertices. So, adjacent vertices, adjacent vertices, adjacent vertices. So, it is a complete subgraph, and it is an independent set in a graph mean set of pairwise non-adjacent vertices. So, example here x, y, u, x, y, u, these are a click because joined together, and u and w are independent set, okay, separately, right. Next, bipartite graph. A graph G is a bipartite if V of G is a union of two disjoint independent set called a partite set of G. So, next the vertices can be partitioned into two sets such that each set is independent. So, next one is a matching problem. So, you take a boys and then girls, and what are all the things match from domain to codomain. So, this 1, 2, 3, 4, here 5, 6, 7, 8, 9. So, 1 may be pair to 5 and 6, 2 may be pair to 5 and 7, 3 may be pair to 7, and 4 to 8 and 9. So, sometimes it may be matching. Job assignment. So, see the workers and jobs are the two categories. So, if workers can do all the types of the job, therefore, it connected to all the 4 vertices, and similarly second worker also do all the pairs of the jobs, and third and fourth also all the pairs of the jobs. So, this is a way we can draw a graph, right. Now, chromatic number of a graph may be written as x of G is the minimum number of colors needed to label the vertices, so that the adjacent vertices receive the different colors. So, here blue mean green, once green and this one is joined mean a different color you have to give, and here two are different because joined with an edge, and red and blue are here these two vertices 3 and 4 are adjacent, therefore, different color should be there. 2 and 4 are different, they have a different colors. Now, the maximum possibilities of color we can use 3, that is called as chromatic number of a graph. Next, maps and coloring. A map is a partition of the plane into connected region. Can we color the region of every map using at most 4 colors, so that a neighboring region have different colors. Map coloring is a meaning of graph coloring. A region mean a vertex, adjacency mean an edge. Next, scheduling and graph coloring. Two committees cannot hold meetings at the same time if two committees have a common member. So, that is the meaning of what committee 1, committee 2, and having a common member can have the meeting. So, it cannot hold meeting at the same time, but if can, then they have a common member, that is the meaning of scheduling and graph coloring. Next, model based on the scheduling graph coloring. One committee being represented by a vertex, and edge between the two vertices if two corresponding committees have a common member, two adjacent vertices cannot receive the same color. This is a scheduling and graph coloring. Scheduling problem is equivalent to graph coloring. You take a committee 1 and committee 2 because they have a common member, they are adjacent to one another, therefore, they have a different color. And committee 2 and committee 3 are adjacent, therefore, different color, but committee 1 and committee 3 are different, therefore, what color we used in committee 1, then we can use the committee 3, therefore, maximum 2 colors we can use of different 3 peoples. So, common member different colors, that is a things we have to use. So, if it is no common, same color we can use, or same time or same slot you can use it. Now, path and cycle. So, let us start with the path. Suppose you take a vertex A, B, C, D, E. So, there is a path that is a sequence A to D, right, and then D to C, and then C to B and then B to E. So, this is a path. Now, you take A, B, D, A, B, E, D, C, B, E, D. There is not a path. So, it is a walk. So, that is the difference between path and walk. Okay. So, path is meaning a sequence of distinct vertices such that two consecutive vertices are adjacent, then it is called it as a path. But walk is not a path. Next, another example, cycle. Cycle, a closed path. Cycle mean is a closed path. Example, A, D, and then C, and then B, and then E, and then A. So, this is a what? Closed path. Therefore, it is a cycle. Next, subgraph. A subgraph of a graph G is a graph H such that V of H is subset of V of G. The vertex set is a subset of vertex of all the set. Edge set is a subset of edge of G. So, assignment of endpoints of each edge as the same in G. So, this is a subgraph. You take a original graph, you take only one edge D and C, that is also subgraph of G. Suppose you take the picture, one of the picture from the G is AB and ED only take it. This picture is taken from G is called it as H2 and H3 we can disjoin AE separate and BCD separate it, then it is also a subgraph of a original graph G. Now, we have three subgraphs of G. Next, connected and disconnected. So, there exists at least one path between two vertices. So, one path, this is a path. Path mean a wedge, that is a vertex connected with the edge is a path and joined with another vertex. So, there exists at least one path between two vertices. Disconnected mean they have no path. Here H1, H2 are connected, whereas you take H3 they have a disjoin, therefore it is a disconnected. Now, adjacency and incident. Adjacency means you take Vj and Vk, and Vj and Vk are connected and with along with the edge. Therefore, it is what? The EI is an edge whose endpoints are Vj and Vk, then it is said to be what? Adjacence. Next, the vertex Vj and Vk are said to be adjacent. The edge EI is said to be incident upon Vj. So, if you take a Vj and connect it with the edge, you do not take Vk, then there is called it as incident. So, this is incident mean Vj and EI connected is said to be incident. Next, degree of a vertex Vk is a number of edges incident upon Vk, it is not d of Vk. So, here d of Vj is only one edge connected, therefore, d of Vj is equal to 1. D of Vk and d of Vk is connected with Vj, therefore, it is also 1. Therefore, degree is each 1. Next, adjacence matrix. You take a graph G, G is consist of vertex and edge. Now, number of vertices is said to be cardinality of V equal to n. Number of edges of E is said to be m. Now, adjacency matrix of G is A of G is written by n cross n matrix, in which entry Aij is the number of edges in G with endpoint Vi, Vj. For example, you take a graph this. Now, how many edges here? A, B, C, D, E, totally 5 edges. How many vertex here? W, X, Y, Z. Now, you have to write W, X, Y, Z, W, X, Y, Z, row wise and column wise. Now, W is connected with the W, any loop is there? No, therefore, put 0. W is connected with X, yes, A, only one edge connected, therefore 1. and W is connected with Y, yes, 1. W is connected with Z, no, therefore 0. All of you follow me? Now similarly go to the second, X vertex you take it, X vertex. X is connected with the W, yes, 1. X is connected with Y, yes, one is X2YC and X2YD. So, 2 edges connected, therefore, X2Y is 2. Now, X is connected with Z, no, therefore 0. So, that is the meaning of this row. Similarly, go to the Y, and Y is connected with the W, yes, 1. Y is connected with X 2 times 2. Y is connected with Y, no, 0. And then Y is connected with Z, yes, 1. Similarly, you go to Z, Z is connected with W 0, Z is connected with X 0, Z is connected with Y 1, Z is connected with Z is 0. Next, incident matrix. Let the G is a V comma E, therefore coordinate of V equal to N, coordinate of V equal to M. So, incident matrix M of G is a N by M matrix in which the entry EMIJ is 1 and VA is the endpoint of EA and otherwise 0. Now, we have a matrix like this, graph is like this. Now, W is connected with W and A, they are what vertex W is what having the edge proceeding, therefore, incident with W, therefore, W and A is 1 and WB, yes, 1. WC, no, therefore 0. W and D are connected, no, 0. W and E are connected, no, therefore 0. So, like that we have to go to the what connection between one vertex to the edges, that is called it as incident matrix. So, like that you take XY, we have 1 0 1 1 0. Similarly, Z we have like this, and then Y Z. So, it is not XY, it is Y, it is Z. So, this is a way we can form a what incident matrix. Next, isomorphism. Isomorphism mean what? You take a graph, this is a graph G and H is a graph. Now, what? Two graphs are isomorphic if the edge set is what? Mapping from one to domain to codomain and should be bijective. So, simple graph H is bijective. Bijective means one-to-one correspondence, vertex to vertex, edge to edge, that is called it as a bijective. So, V of G to V of H and connection of UV to edge. So, W, X, Y, Z is a one graph, and here also what C, A, D, B. Now, the mapping is for first one W, X, Y, Z, right, corresponding what map W is mapped to C and X is maps to B and Y is maps to D, Z is maps to A, and similarly F2 is W, X, Y, Z and backtrack A for W, X to D, Y to B and Z to C. Now, complete graph. Complete graph is a bipartite graph, complete bipartite graph and biclick. So, complete graph is a simple graph whose vertices are pairwise adjacent, and complete bipartite graph is a simple bipartite graph such that two vertices are adjacent if and only if they are different partite graph. So, this is a complete graph. So, any vertex any vertex take it and connect it with all the other vertices, then it is said to be complete graph. Bipartite means one set is like this, another set is like this, all the possibilities of vertex of the opposite is connected from one vertex. See here, this V1 is connected with what V1 star, V1 dash, V2 dash, V2, V3 dash, then it is a bipartite. Next, Peterson graph. Peterson graph is a simple graph whose vertices are 2 element subset of 5 element set and whose edges are pairwise disjoint of 2 elements. So, this is an example. Assume that the elements 1, 2, 3, 4, 5, then 2 elements 1 and 2, 1 and 3, and then 1 and 4, 1 and 5, 2 and 3, 2, 4, 2, 5, 3, 4, 3, 5, 3, 4, 5, 4, 5 like that. So, these ways you have to connect, then it is said to be Peterson graph. So, 3 drawings a Peterson graph. So, these are all the different types of drawing a Peterson graph. Theorem: if 2 vertices are non-adjacent in the Peterson graph, they have exactly one common neighbor. If there is no connection, no problem. If join one common element, so like that 3 elements in these vertices totally x, y, x, z, u, v, since 5 elements totally 5 to 3 elements left, hence exactly one of this kind follows. This is a proof. Next, girth. Girth is the length of the shortest cycle. If no cycle, then girth is infinite. Next, girth and Peterson graph. So, Peterson graph has girth 5. So, proof is if it is simple and no loop, no cycle, therefore, cycle of length 1, very simple. If simple and no multiple and no 2 cycle. If you take 5 element, no 3 pair disjoint 2 sets, no 3 cycles. So, according to previous theorem, 2 adjacent non-adjacent vertices has exactly one common neighbor. So, number of 4 cycles. So, no 4 cycles. Therefore, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2 is a 5 cycle will come. Next, walk. A walk is a list of vertices edges, say one graph. So, here one graph is there. You take this graph you take it, walk. So, here you have to start this, go walk like that. So, this is a way we can go the walk. So, walk is a the list of vertices and edges V0, E1, V1 and so on Ek, Vk such that 1 less than equal to I less than equal to k, the edge Ei has an end points and V suffix I minus 1 and Vi. So, the trial, a walk has a no repeated edge, then it is said to be trial. Next, path, U and V are a walk and UV is a trial as a first vertex U and last vertex V. These are its endpoints. A UV path is a trial and no repeated vertex. So, a length of a walk is a trial, path or cycle, its number of edges. So, a walk or trial is a closed if its endpoints are the same. Next, lemma. Every UV walk contains UV path. Proof. Use the induction on the length of L of U, comma V walk W. Basis step is L equal to 0, having no edge. W consists of single vertex U comma V. This vertex UV path of length 0 and this is to be continued. Next, every UV walk contains UV path. By induction hypothesis, let L is greater than or equal to 1, this is the figure, you have to take it and then suppose that the climb holds for a walk of length less than L and W has no repeated vertex, then its vertices and edges form UV path. If W has a repeated vertex W, then deleting the edges and vertices between the appearance of W, leaving one copy of W yields a shorter UV walk W contained in W. And by this induction hypothesis, W contains UV path P and this path P contained in W. So, this is an example. If you delete it, disconnect, if you have this, then we have the path and it will be a walk. The walk is a path. Next, component. Component of a graph are its maximal connected subgraph. So, you take one graph and disconnect it and all these are connected, then it is said to be component. So, component of a graph is a trivial if it has no edges, otherwise it is non-trivial. So, isolated vertex is a vertex of degree 0. Next theorem, every graph with n vertices and k edges has its at least n minus k components. So, an n vertex graph with no edges has n components. Each edge added reduces this by at most 1. If k edges are added, then the number of components is at least n minus k. Theorem: every graph with n vertices and k edges has at least n minus k components. For example, here n equal to 2 vertices and k equal to 1 connected, therefore 1 component. Here n equal to 3, number of vertices 3 and k equal to 2 edges, therefore 1 component. Here we have possibilities of n equal to 6 and k equal to 3 and 3 components generated. Here n equal to 6 and k equal to 3, 4 components generated. Now, cut edge, cut vertex. Cut edge or cut vertex of a graph is an edge of vertex whose deletion increases the number of component. Suppose if you cut it, then it will be component. So, here this is not cut vertex, here it is a cut edge possible, here we have a cut vertex possible. So, these are all the cut it, then cut vertex and cut edge will possible. So, if a graph disconnect with one edge or g minus m, then subgraph obtained by deleting an edge E or set of edges M. And then if G minus V represent cut vertex, deleting the vertex or set of vertices. So, this is the example of what cut edge. So, if you delete the vertex, then cut vertex, deleting the edge is said to be cut edges. Next, induced subgraph. An induced subgraph is obtained by deleting a set of vertices with g of t for g minus t, where t equal to v of g minus t, and g of t is a subgraph of g induced by t. Now, here assume t equal to a b c d, and then this is a graph and we have the induced of these vertices. Next, induced subgraph of more examples. G2 is a subgraph of G1 induced by ABCD, and G3 is a subgraph of G1 induced by BC, and G4 is not a subgraph because it is not in the structure of the same as in the G1. Therefore, G1 and G4 is not a subgraph of induced by G1. Next, induced subgraph. A set of vertices is an independent set if and only if subgraph induced by it has no edges. So, here G1 and G3, here G3 taken from the G1, but no edge is connected from this, therefore, it is induced. Next, based on this theorem, an edge E is a cut edge if and only if E belongs to no cycle. So, proof is very simple. You take an edge E is x comma y be an edge of the graph, H is a component of E, and deleting E affects no other component. Therefore, H minus E is connected if and only if E belongs to cycle. First, suppose that H minus E is connected, this implies H minus E contains an x comma y path. So, this path completes a cycle with E. Next theorem, and edge E is a cut edge if and only if E belongs to no cycles. Choose the edge E lies in the cycle and u comma v in V of H. H is connected, H has uv path, P does not contain E, then P exists in H minus E. Otherwise, by symmetry that x is between u and y on P and H minus E containing u, x path along P, the transitivity of the connection relation implies H minus E has a uv path. So, another theorem, an edge E is a cut edge if and only if he belongs to no cycles. So, this is an example of what cut edges, therefore, no cycle will form. Next, every closed odd walk containing an odd cycle. So, use the induction on the length L of a closed odd walk W, L equal to 1. A closed walk of length 1 traverses a cycle of length 1. So, we need to prove the climb holds if holds for the closed odd walk shorter than W. Next theorem, every closed odd walk contains an odd cycle. Suppose that climb holds for the closed odd walks shorter than W. If W has no repeated vertex, then W itself forms a cycle of odd length. Otherwise, we have to prove if repeated, W includes a shorter closed odd walk. By induction, the theorem hold. If W has a repeated vertex V, then we view W as a starting at V and break W into two V and V walks. Since W has a odd length, one of these is odd and other is even. So, the odd one is shorter than W. By induction hypothesis, it contains odd cycle and these cycles appear in order in W. So, every closed odd walk contains an odd cycle. This is an example of odd equal to odd plus even. So, this is the meaning of how to convert every closed odd walk containing odd cycle. Next, a graph is a bipartite if and only if it has a no odd cycle. So, you take an example, ABCD is one example of a graph and another set of graph is like this. Now, we have a graph as a no odd cycle. So, FAEBDC and this is a bipartite and it has a no odd cycle. Next, a graph is a bipartite if it has a no odd cycle. Proof is G be a graph with no odd cycles and G is a bipartite. By construction, the bipartition of each non-trivial component H, you take V in VH and f of V the minimum length of U and V path. Since H is connected, f of V is defined V in V of H. So, this way we have to connect U in terms of VV dash. So, a closed walk using a shortest UV path, the edge VV dash within X or Y and reverse the shortest UV path. We have X and Y are independent set. So, a graph is a bipartite if it has a no odd cycle. So, G be a bipartite graph, every walk alternates between the two sets of bipartition and every return of the original partite set happens after an even number of steps. So, G has no odd cycle. Next, Eulerian circuit. A graph is Eulerian, it has a closed trial containing all edges. So, we call a closed trial a circuit when we do not specify the first vertex, but give the list in the cycle order. So, Eulerian circuit or Eulerian trial is a graph, it is a circuit or trial containing all the edges. Next, even graph, even vertex and minimal path. A graph is said to be even graph if the graph with a vertex degree all are even. A vertex is odd, then when its degree is odd. So, a maximal path in a graph, G is a path P in G that is not containing in a longer path. So, when graph is a finite, no path can extend forever. So, maximum path exists. Next, based on the lemma, every vertex of a graph G has a degree at least 2, then G contains cycle. Proof, let P be a maximal path in G, let U be an endpoint of P. Since P cannot extend it, so every neighbor of U must already be the vertex of P. Since U has a degree at least 2 and it has a neighbor with V and V of P and edge not in P, therefore, UV completes the cycle. A portion of P from V to U is if it is possible and it is impossible and we have a must. Next, a graph is Eulerian and if and only if it has at most non-trivial component and its degree all have the even degree. So, proof, necessity, suppose that G has an Eulerian circuit, each passage of C through a vertex uses 2 incident edges and the first edge is paired with the last at the first vertex. Hence, every vertex has an even degree. Also, 2 edges can be in the same trial only when they lie in the same component. So, there is at most one non-trivial component. Next, a graph is Eulerian for at most a non-trivial component and then it has a vertex of even degree. Sufficiently, assuming that condition is hold, we obtain an Eulerian circuit using the induction on the number of edges m by basic step m equal to 0, then the closed trial consists of one vertex suffices. Next theorem, a graph G is Eulerian if and only if at most one non-trivial components and its vertices all have a even degree. So, we can with proof of lemma of a non-trivial component as a cycle C and the graph obtained from G by deleting E of C dash, and then C has a 0 or 2 edges at least each vertex. Therefore, the component G dash is also even graph. Since each component is also connected and has fewer than m edges, so we can apply the induction hypothesis to conclude that each component G dash has an Eulerian circuit. So, a graph is Eulerian if and only if at most non-trivial component all that have even degree in different ways of a sufficient part using the induction m is positive combined into the Eulerian circuit of G. We traverse C, but when the component of G dash is entered for the first time, so we detour along an Eulerian circuit of that component. So, this circuit ends at the vertex where we began the detour. When we complete the traversal of C and we have completed an Eulerian circuit of G. Next, proportion, every even graph decomposes into cycle. Next proportion, if G is a simple graph in which every vertex has a degree at least k, then G contains a path of length at least k. So, if k is greater than or equal to 2, then G is also containing a cycle of length at least k plus 1. So, once you know the ideas, then that is enough for the statement. So, here you having the endpoint and has a maximal path, P does not extend, therefore, it has a neighbor. So, U is in the neighbor, therefore, U has at least k neighbors and the graph is simple, therefore, it has a k vertices other than U and it has at least k. Next, like that we can go for G is a simple graph in which every vertex has degree at least k, then G contains a path of length at least k, k greater than or equal to 2, G is also contains a cycle of length at least k plus. In another way we can prove like this. Next, degree of a vertex in a graph is written by d of v. So, the number of edges incident to v except each loop at p count twice. So, if you take A have how many edges connected with other vertices, therefore, here 1, 2, 3, therefore, degree of A is equal to 3. So, like that maximal degree of is denoted by capital delta G and minimum degree is small delta G. Now, we have a vertex B, degree of B is 3 and C you take it vertex C is having degree 2 and delta of G is maximum B is 3, minimum degree of delta is 2. Therefore, this is the meaning of capital delta and small delta of degree. Next, regular, and if capital delta and small delta are equal, then the graph is said to be k regular.